We've talked about ionic bonds and covalent bonds, and we have to talk about bonding in metals. We've mentioned this before, but here's the whole thing. The electron C model for bonding of metals. So metals have low ionization energies. It's easy to remove electrons from them. So in a metallic solid, each metal atom is donating electrons to this electron C, or a big pool of electrons. Mostly it's the valence electrons that are going out. So in this illustration here, we have a bunch of sodium atoms, and they each donate one electron to the C. They send out one electron to play. That electron is free to move around. Overall, though, this piece of matter has a neutral charge because there's an equal number of electrons and protons. So these positive sodium ions are attracted to each other by this sea of electrons. The sodium can conduct electricity because the electrons in that pool, that ocean, are free to move. And so they can move, and movement of electrical charge is conductivity. The electrons can move. This also explains the properties malleability and ductility that most metals have. If you hit a metal with a sledgehammer, you may put a dent in it, right? And if you keep hitting it, you could hammer it flat and change its shape. You can do that because when you put stress on this, the atoms will just move out of the way, and they're still attracted to the electrons around them, and so it's all fine. In an ionic compound, when you hit it with a sledgehammer, when you cause a little bit of distance change between those oppositely charged ions, you're going to dramatically change the force of attraction, and it'll probably shatter. Metals don't do that. Any questions? And then this is just an interesting bit about ozone. So we've looked at the Lewis structures for ozone and for oxygen. Ozone is O3, and it has resonance, and so we could represent it that way as it's got two identical bonds. Those bonds are between a single and a double bond. You can call it a 1.5 bond, if you like. If this is a 1.5 bond, is that weaker or stronger than a double bond? It's weaker, right? It's going to be between a double and a single in strength. So up in the atmosphere, there is ozone, and there's ultraviolet radiation coming from the sun. The ultraviolet radiation has enough energy to break this in-between bond in ozone. The UV does not have enough energy to break a double bond in oxygen. So what happens is ozone molecules absorb some of the UV light coming in, and they break into an oxygen molecule and an oxygen atom. And they absorb energy when they do that. So that causes less ultraviolet radiation to actually make it to the surface, where it gives me a really bad sunburn. The oxygen atom and the oxygen molecules then will reform the ozone, and then it's out there to absorb another photon of UV light. That's why ozone is important.
So how is that being damaged?
How is that being damaged? That's an excellent question. Chlorofluorocarbons interfere with this cycle of reforming the ozone, and so messes everything up.
Which is what's in spray cans and stuff like that.
Yeah, it's aerosols in aerosol cans, the propellants, and then like Freon and different refrigerants.